Okay, so last time we left off with this exercise where f of x was 2 over 3x minus 1, and we wanted to compute the inverse of that function. So we first write this as y equals 2 over 3x minus 1, and then we swap x and y to get x is equal to 2 over 3y minus 1. If we cross multiply, we get x times 3y minus 1 is equal to 2, or 3xy minus x is equal to 2. So then we get 3xy is equal to x plus 2 by adding x to both sides here. And then we divide by 3x on both sides to get y equals x plus 2 divided by 3x. So that's our candidate and what's going to be our solution for the first part of this. So this is our f inverse where our f of x was 2 over 3x minus 1. And what we want to do is we want to check that f composed with f inverse of x is x, and f inverse composed with f of x is equal to x. So this is what we want to check. So let's go ahead and start with the first one, f of f inverse of x, that's f, and then replace x with f inverse, hence we get 2 over 3 f inverse of x minus 1, where f inverse was x plus 2 over 3x, so x plus 2 over 3x, and then minus 1 here. So the 3's here cancel to get us just 2 divided by x plus 2 divided by x, and then minus, I'm going to put a common denominator by multiplying the top and bottom by x here. So what do we have? We have 2 divided by x plus 2 minus x over x. These x's cancel, the x and the minus x, and we're left with 2 divided by 2 over x, which is the same as 2 times x over 2, which is x. So that shows that f of f inverse of x is equal to x, and we want to go now the other way. So f inverse of f of x, that's f inverse applied to f of x. So where f inverse was right here, x plus 2 over 3x, we're going to replace the x's with f of x's. So we're going to get f of x plus 2 over 3f of x, where f of x was 2 over 3x minus 1. So what do we get here? We get 2 divided by 3x minus 1 plus 2 all over 3 times 2 over 3x minus 1. Okay, well, we have to put a common denominator on the top. Remember, 2 is the same as 2 divided by 1. So the common denominator here is just 3x minus 1. Let me put kind of a giant denominator here. In the bottom here, by the way, we have 6 over 3x minus 1. What we're doing right now is adding up these guys, which will become what this is. Well, we have a 2 over here because that's already divided by 3x minus 1. Here I have to multiply by 3x minus 1 over 3x minus 1 to get my common denominator. So I have plus 2 times 3x minus 1. Okay, it looks worse than it is, I assure you. What do we get here? We get 2 plus 6x minus 2 divided by 3x minus 1 all over 6 divided by 3x minus 1. The 2's here cancel, and we're left with 6x over 3x minus 1 all over 6 over 3x minus 1. And hopefully you see that, you'll see in a moment that this works out just nicely. If you have a fraction over a fraction, it's the numerator here multiplied by the reciprocal of the denominator. And so the 3x minus 1 cancels with the 3x minus 1. The 6 cancels with the 6. And we are left with x as desired. Okay, so that was the exercise that I left from last time. To conclude 2.8, I just want to give two last examples. One is sort of things that are not inverses of each other. All the examples we've been doing have been things that have been inverses of each other. It's actually much easier to come up with things that are not inverses of each other. And let's just give one example. Say 3 over x is f of x, and g of x is 2 over x, say, for example. And I claim these are not inverses of each other. How do we check? Let's take f composed with g of x. So if this is not equal to x, then they're not inverses of each other, right? Because that's one of the defining properties. So let's take f of g of x, which is 3 over g of x. If that's not equal to x, then they're not inverses of each other. Well, this is 3 over 2 over x. This is 3 times x over 2, which is 3 halves x. 3 halves x, well, that's not exactly x. And hence, they're not inverses of each other. Not inverses. Okay. So there's lots of examples which you can do like this, but it's just one example I thought I would do. I want to do one last example, which is an example of a domain restriction. And this is an important one because it does come up. So let's let f of x be the square root of x minus 1. Now, if we graph this, this is just a horizontal shift 1 unit to the right of the square root of x, and you get this graph. And this graph is 1 to 1. Crosses the horizontal line test, so this is 1 to 1. Is 1 to 1. So we should be able to compute the inverse, so let's compute it. We swap x and y to get x equals root y minus 1. And we square both sides to get y minus 1 is equal to x squared, or y is equal to x squared plus 1. So f inverse of x is x squared plus 1. Well, let's look at the graph of f inverse here. This is the x squared graph bumped up by 1 unit. We have this graph. But this graph fails the horizontal line test. But according to our procedure, it should be the inverse of this. It should be invertible. It doesn't make sense, right? Like so note here that usually the inverse of f inverse of x is f of x. That's what we, if the inverse of f is f inverse, it goes the other way too. The inverse of f inverse is f. Hopefully you caught that. But if this fails a horizontal line test, that says we can't even invert this function. So something is a little weird. So what is going on? Let's go back and kind of start over and go a little bit more carefully. What is the domain here? The domain of f, this is 1 to positive infinity. And the range, the y values, the range is all y values bigger than 0, right? All y values bigger than 0 is what we attain. Well, what does that mean for f inverse? Remember that we also have this property. So there's this important property which I stated at the very beginning of this section. So there's a property that the domain of f is the range of f inverse. And the range of f is the domain of f inverse. So this is a very important property. So what is this saying for f inverse? What is its domain? So let me get rid of this graph now, because it's going to be a little different now. So we did, now let's say we got to this point where we computed f inverse. What is the domain? Well, the domain of f inverse is the range of f. What was the range of f? It was 0 to infinity. So we restrict our domain to 0 to infinity. And the range of f inverse is 1 to positive infinity. Remember, this domain is what x values we're allowed to plug in. So let's plug in now only x values. These are our x values that are allowed to be plugged into f inverse. So let's plug in just a few values bigger than 0. 0, 1, and 2. Let's just do those. What are our y values here? Our y values here are 1, 2, and 5. So what does our graph look like actually? Let me get rid of this now, because this is now no longer going to be relevant for us. What is our graph? Well, I have the point 0, 1. I have the point 1, 2. And I have the point 2, 5. This on its own it does pass the horizontal line test. So this is the graph of f inverse. Let me go back and graph the graph of f. Remember, f of x was the square root of x minus 1. Notice we have the point here 1, 0, 2, 1. Right? If you plug in 2 here, y equals 1. And if you plugged in 3, 4, 5, you would get 2. So x equals 5. Here we get y equals 2. So at 5 we have 2. And notice here, these things are symmetric about the line y equals x, which is exactly what we want. The only thing that had to happen was this domain, the domain of f inverse, we had to notice that it actually was restricted to just 0 to infinity because it came from the range of the original function f. And that allows the function to both functions, f and f inverse, to be 1 to 1, which is always true. They both should be 1 to 1. They both should pass the horizontal line test. And so that was the point that I wanted to emphasize here, that the domain here is a restricted domain. In general, if we have a function, I'll call it g of x equals x squared plus 1, the domain here is all real numbers. It's everything. You can plug in any number you like. whereas here, the domain got restricted to 0 to infinity. So that's an example that's important, that sometimes when you restrict a domain, you get an invertible function. Okay, so this is the end of 2.8. We'll stop here for now and continue with the next video next time.